Afternoon, everybody. I think we're starting to hit our typical amount of people for the week. Thanks everybody for joining in. Uh, and we had a couple of questions come into me personally instead of the mailing list about Michael's materials from last week. I did get those updated, so if you haven't gotten them yet, go back and look at the regular folders. The slides should be in there as well as um, the videos if you wanted to watch them outside of YouTube. So those should all be updated. This week's talk is going to be from Vardan Gyurjyan from JLab, and he's going to be talking a little bit about EJFAT, which stands for the ESNet JLab FPGA Accelerated Transport project. And it's specifically going to be talking about the use case of using this for nuclear physics data processing. And Yatish is also on as well as a member of the project, and he'll be able to help answer a little bit of the networking questions. So I'm going to turn it over to Vardan to get started.
Okay, good morning. Let me share my screen. Okay, hope this is okay. So before we begin, let me briefly introduce myself. So I am Vardan Gyurjyan. I'm a staff scientist at Jefferson Lab. My background is in high energy and nuclear physics. I studied high energy monochromatic radiation as part of my PhD. It was ages ago. And then worked on neutron structure functions, nuclear form factors. So over years, I have been involved in designing, simulating, building, and testing the Hermes calorimeter at DAISY at CERN, as well as a large angle calorimeter for class detector at CBUF. In addition to my physics background, I also have a foundation in computing. I have a master's degree from Soviet era here, Polytechnic University from Yerevan. So since 1997, I joined Jefferson Lab. I have contributed to software development for data acquisition, data analytics, and experimental control systems. So you might find me wearing two hats, physics and computing, sometimes both at once during this presentation. So my subtitle of this presentation says new generation experimental physicists are choosing streaming. And while my white hair, you see my white hair, it's just says completely opposite, but I'm young in heart. I just want to mention that the results I'll be sharing were presented at supercomputing this year, last year, 24. So I'll be using slides from that talk. So my sincere apologies to those who have already seen them. So that said, I really hope this setting allows for more relaxed and open discussion, and I'd love to hear any questions or thoughts you might have. So here is my outline of my presentation. I'll introduce Jefferson Lab and its broader role in experimental nuclear physics research. The main focus will be to highlight and demonstrate the capability of EJFAT system, along with supporting technology for resource allocation, orchestration, and data stream processing application design. And then this will culminate in showcasing a concept validation experiment. It's the recording, but it's a real experiment where data for one of the JLab experiments was processed remotely in streaming mode across the country. So Jefferson Lab, or Thomas Jefferson National Accelerator Facility, is a relatively young DOE national lab at just 40 years old. It's a leader in nuclear physics, housing a unique electron accelerator with 100% duty factor. And this is our pride. So unlike the LHC, which has duty factor below 40% due to the particle bunch and beam-based operations, with data acquisition occurring only when these particle bunches collide at specific points. Jefferson Lab operations are totally continuous, so we get data continuously as long as machine is working. It also co-leads the Electron Ion Collider project, EIC project, with Brookhaven, and spearheads the High Performance Data Facility project collaboration with LBNL. This is a project which is a significant component of the DOE's Integrated Research Infrastructure Initiative. So JLab has 4 experimental halls or stations labeled A, B, C, and D, each equipped with specialized detectors that support a wide range of nuclear physics studies. This includes research on quark-gluon interactions, the structure of the protons and neutrons, nuclear form factors, hadronization, short-range correlation, and exotic matter states. This is absolute entire region. As with any other scientific enterprise, we witness that data exponential increase, so-called scientific big data 3V pressure. I'm pretty much sure now the V's, number of V's are increasing, but those are 3V's are volume, velocity, and variety. The data expansion is due to continuous upgrades to the detectors and accelerators by increasing luminosities. The grand challenge initiative at Jefferson Lab is to address data challenges in transitioning from our nuclear experiment from traditional triggered approach to triggerless or streaming mode. These goals involve not only streaming data acquisition, but also improving detector calibration and data processing, including the entire data lifecycle from acquisition to calibration and real-time data stream processing. So now the question, before answering this, the question, how can streaming increase science outcome? It is important to realize that scientific experiments are expensive undertakings, so specifically high energy nuclear physics experiments, which are costly to build and operate. For example, an hour of beam time at Jefferson Lab costs $10 or above $10,000 when factoring in the personnel, electricity, maintenance of the superconducting radio frequency cavities. Given this expense, it's crucial to maximize the physics insight from each experiment. So traditional triggered experiments define conditions to study phenomena of interest by using a so-called level 1 triggering system, where signals from fast detector components, so fast I means that those are detectors having fast response time to leptons or hadrons passing through the detector media, are passed through level 1 fast electronics for coincidence and anti-coincidence to select particle in special geometrical location with desired energy deposition and timing. It is important to mention that anything not passing so-called level 1 triggered decision is discarded and is lost forever. So it is important to make this decision fast and accurate. One way to increase the accuracy and efficiency of the trigger-making decision is to add more detectors to the decision-making process, not only fast detectors, but also slow detectors like drift chambers. Adding more detectors to the level 1 trigger will increase level 1 latency, which is one of the main contributors to data acquisition, so-called dead time. This is a time when the entire detector, figuratively speaking, is blind what is happening in the experiment. Here on this right, I apologize if it's not you cannot see it well, but it is a dead time of a recent experiment at JLab that took data for about 1.5 months. The average dead time is about 10%, as you can see, meaning that we were missing $1,000 per hour worth of science, assuming the cost of the 1 hour beam time. For a typical running period at Jefferson Lab, we can have 150, 180 hours per year. This adds up to be millions of dollars worth of science missed. So streaming data acquisition and data architectures allow the elimination of that time, that saves money, and increase efficiency for event identification by incorporating all detector components. Yet the main advantage, if you ask me, of the streaming system is that we are capable of preserving data with minimum processing, minimum filtration from all detector components. not doing any kind of physics, deferring data analytics to software processing, enabling future physicists with young physicists, with fresh perspectives to mine data, looking for different signatures, extracting novel insight into nature. Time after time, we see that excited physics happen when we are not looking into it. So it seems it's a no-brainer. Why we were not considering streaming earlier? The main barriers were likely high memory costs and network performance limitations, both of which have followed trends similar to Moore's law. Over time, we've seen significant drops in memory costs alongside exponential increases in network transmission speeds, with advances in Ethernet standards now reaching 100 gigabits and beyond. You can see the upper right, and lower. These technologies strides give rise to memory data processing workflows and distributed data stream processing workflows. Frameworks like Apache Kafka, Apache Flink, Spark streaming have become increasingly popular. In-memory data processing and data stream workflows are now integral part of the distributed architectures and are commonly used across fields like finance and large-scale cloud services. Excuse me. However, in scientific data processing, we often encounter unique requirements that commercial solutions aren't fully equipped to handle. Scientific experiments typically gather data from multiple sources. For example, our experiments have hundreds and almost up to 1,000 crates readout sources. Each of these sources needing to be precisely linked to explore a specific physics phenomena. This linking or genetic correlation relies on experiment-specific metrics, such as triggering defined events or using digitized electronics to apply globally synchronized timestamp on each sample, digitized sample. When transmitting this data across wide area networks, we need network solutions that recognize these unique identifiers and can shape, sort, and forward data based on experiment-specific metrics. Given the compute-intensive nature of scientific processes, the dynamic load balancing is also very essential to ensure optimal and efficient use of the computational resources. So this brings me to introduction of the EJFAT system, ESNet JLab FPGA Accelerated Transport system, specifically designed to meet the rigorous demands of high-volume data stream processing in scientific workflows. This system integrates data event-aware network shaping and forwarding capabilities while leveraging unidirectional UDP streaming. Okay, so the EJFAT load balancing completely separates the IP addresses of the compute nodes from those of the data acquisition. Essentially, the DACs only need the IP address of the load balancer only. When data packets leave the load balancer, the source IP is set to the load balancer, IP address of the load balancer, and the destination IP is dynamically assigned to the compute nodes. This IP address reassignment done on the fly at a very high rate, every few nanoseconds, suggests the use of FPGA and is one of the unique capabilities of contemporary network transport systems. These nodes addresses are initially downloaded, the right side nodes, processing nodes, initially downloaded to the load balancer as the result of the computing node registration process at the experiment start and at runtime, making the system fully elastic. Mostly importantly, the elastic IP space of the computing resources remains completely hidden from the DAC, maintaining clear separation. As the experiment progresses, some compute nodes will process the data faster than the others. To accommodate this, the load balancer includes a mechanism to adjust its workload distribution to prevent slower nodes from becoming overloaded and to keep faster nodes operating at peak performance. So the unidirectional UDP transport is achieved through the dedicated application layer protocol for segmentation and reassembly, which functions directly between DAC and component nodes, bypassing the load balancer involvement. Within this protocol, each doc event data bundle is assigned to a unique event ID and data ID. The colors here are data ID. An event ID is the science marker I was talking earlier. Each event data bundle is then divided into smaller data segments, ensuring each fits within the 9 kilobyte maximum packet size. These segments share the same event ID in the load balancer protocol header to ensure they reach the same compute node for reassembly. Additionally, an entropy field is assigned, either randomly or sequentially, across all segments of a bundle, further ensuring they arrive at a single UDP receiver on the design compute node for optimum reassembly or faster reassembly, multi-threaded reassembly. This approach allows for both seamless delivery and accurate reassembly, which is essential for maintaining the integrity of the experiment's data flow. Excuse me. I apologize. I'm doing this presentation from the cubicle, and there can be interferences. I apologize for any inconvenience. So now about our data stream naturally assumes some kind of level of spontaneity and dynamism. You can say impulsivity, if that's a word, in how data flows through the system. Unlike traditional batch processing, where data is gathered and processed in bulk at scheduled intervals, data stream processing is dynamic and continuous. Data flows in real time, often dynamically defined pathways, and must be processed on the fly. The dynamic nature of the streaming allows the data flow to be split into multiple branches, each potentially serving different purposes and destinations. These branches can be created based on data characteristics, processing requirements, or priority levels, calibration, data quality assurance, etc. For example, one branch might handle fast real-time analysis for, again, QA, for example, or steering the ongoing experiment in real time, while another may store data for deeper, longer-term analytics. Additionally, the spontaneous nature of streaming means data can be fed to randomly distributed data processing endpoints, servers, and processes distributed across various geographical location, or can be cloud infrastructures as well. These processors don't have to be pre-scheduled. Instead, the system dynamically decides where to route the data based on factors like load balancing, resource availability, or proximity to the end user. In essence, data streaming introduces a powerful capability of adaptive real-time data handling, where branches of processing pipelines evolve as needed and processing units are dispersed and orchestrated to maximize efficiency and responsiveness. This flexibility is a hallmark of modern distributed data stream processing system. In this highly dynamic and elastic environment of data stream processing, data streams, high performance computing, data stream processing, which is in high energy, nuclear physics and biology, any scientific high HPC processing, orchestration of those applications becomes a fairly complex task, requiring automated deployments, scaling and management of applications, and while ensuring they stay running smoothly even during traffic spikes or server failures. To address these requirements, the obvious approach is to containerize applications and use Kubernetes to handle them. Why Kubernetes? Because why to invent a new wheel? Kubernetes is a powerful open source platform that automates the deployment, scaling, and management of containerized applications. It simplifies operations by providing built-in tools for load balancing, service discovery, and scaling. Many DOE supercomputing facilities have increasingly supporting Kubernetes as part of their evolving infrastructure to handle containerized workloads and cloud-native applications. Examples are NERC's Beam platform, OLCF Summit, ILCF Theta, etc. However, the majority of resources of DOE facilities, and not only DOE, are not under Kubernetes control. The JLab, which stands for JLab Integrated Infrastructure Across Facilities, this was the LDRD project that I was leading, and was completed last fiscal year, is designed to evaluate capabilities to combine geographically diverse computing facilities into an integrated infrastructure. An infrastructure that allows dynamic provisioning and use of scheduled or temporarily idled, unallocated resources from various providers. In other words, create a resource pool that combines opportunistic resources from many participating data centers or scheduled resources as well, presented to end user as a single unified compute infrastructure, a new virtual elastic Kubernetes cluster, if you like. So central to the architecture, JLab architecture, is a JLab Resource Manager, JRM, which utilizes virtual kubelet technology to enable Kubernetes environments without root access. JRM is implemented as a daemon that mimics the behavior of the real kubelet. This abstraction allows JLab to treat external services if they were part of the Kubernetes cluster operating in user space, ideal for integrating resources from facilities that are not using Kubernetes. They are not buying into the Kubernetes. So this system also assumes proactive resource acquisition by monitoring available resources, which can also be opportunistic, and runs GRM presenting resources as Kubernetes node in the JLab Kubernetes cluster. Based on user request, user containers are deployed as pods in GRM. An additional level of resource monitoring, resource optimization, and utilization. Excuse me. So on the top of the Kubernetes monitoring resources, it also provides its own monitoring capabilities. So for more technical details, please refer to the Git repository and recent publication accessible from this slide. All right, now let me switch to my physics mode for a moment and walk you through the experiment set up at JLab, specifically the class 12 experiment. That data, which we will be processing remotely using resources spread across NERSC, ORNL, and Fabric. Now, class 12 isn't exactly something you'd find in your garage. It's one of the flagship pieces of experiment at Jefferson Lab, and not of the laptop, tabletop variety. To give you a sense of its scale, what you see here is the installation of one of the 6 sectors of the low threshold Cherenkov counter, which is just one of the many subdetectors of the massive class 12. In this particular shot, we are looking at the installation of a sector 3 of the Cherenkov detector. To the left, you can see the 6 sectors of the time of flight detectors here. This left, with a pre-shower colorimeter detector lined up further back. Up front or to your right, you've got the drift chamber detectors and the central detector right at the interaction point. Though the entire detector is moved in order to make a space for installation. It's a bit like rearranging furniture, but with multi-ton physics equipment. So class, which stands for CBUF large acceptance spectrometer, is unique, and 12 is a detector redesigned for 12 JF, class CBUF 12 JF. Is a unique detector with nearly 4 pi coverage, achieving throughout the configuration of 6 sector-based detector system. So it's fully hermetic detector. It can detect all particles in all directions. So it is achieved, again, having unique, identical sector detector configuration like this one. It's shown in the middle. So this is one sector of detector. It consists of colorimeter and at the very top, and we are going to the lower left. This is colorimeter, which records particle energy deposition and provides coarse position of the timing, achieving approximately half a centimeter spatial resolution and 500 picosecond timing precision. Position to in front, going to the left. This is a pre-shower detector that helps distinguish charged particles from neutral particles. This is achieved because only charged particles leave a small energy signature here, whereas neutrals do not. Following this is the time of flight detector, making the precise detection of the time of each particle. This is about the resolutions can achieve very high to 80 picosecond resolution. To further separate particles, we have low threshold Cherenkov counters. You have seen in this small video the installation of the third sector of this detector that can distinguish between pi and k mesons. And then there comes now 3 layers of drift chambers. Sorry. 3 layers drift chamber for which are measuring drift momentum of the charged particles. These are running. These are detector components which are running within the toroidal magnetic field, and the particles with different momentum will have different trajectories within the same magnetic field. Moving closer to interaction point, a high threshold Cherenkov counter identifies electrons and high energy pions. So we go to 4.9 GeV above particle pion detection here. The interaction region is surrounded by the central detector, equipped with advanced tracking components like micromegas, silicon verticless tracker, and central neutron detector, among others. So the reason for detailed description of this one, of the detector, one sector here, plus the is to introduce ERSAP, a reactive actor-based data stream processing framework, which powers the Class 12 event reconstruction application. On your right here, you see the ERSAP, data flow diagram illustrating its flexible modular design. Each actor in this ERSAP is a specialized processor for the data from a particular detector component. And they are loosely coupled in terms that there's no programmatic dependencies. They can be independently developed. They were independently developed. They can be independently deployed and undeployed, allowing detector-specific processing to be dynamically enabled or disabled in real time. Effectively managing processing, we can effectively manage our processing complexity, which I will describe a little bit later. Notably, within the setup are actors tailored for the EJFAT system. At the top here is the reassembly engine actor, which reassembles EJFAT UDP packets. Those are packetized from the source packets into raw experimental event, initial experimental data, which then flow through the actor chain, triggering processing steps specific to each detector component. At the end of the chain, we have another EJFAT-related actor, which segments the reconstructed or the processed events back into the UDP packets to transfer to other processing, which is data analysis for data quality assurances or calibration whatsoever. So those are the packets we'll send through this another load balancer instance for further processing and data validation and something else. So this is a slide that emphasizes the advantages of this kind of approach, actor-based approach. This is encouraging application design based on independent software artifacts that can be independently developed. So there were so many detector components in this large collaboration of the Class 12, and there were separate groups who were developing their processing, their reconstruction algorithms completely independent. And they had their own choice of their technologies to be used, languages to be used, libraries to be used. And then all these completely independent artifacts or actors will be, this framework can take and put together in a coherent application, which will be functioning efficiently. And this encourages fault tolerance, definitely it is easy to embrace hardware and software heterogeneity. We have AI components in these applications as well. So, and also importantly, it can eliminate long-term commitment to a single technology stack, so you can modernize the application step by step or actor by actor steps. ERSAP framework is designed to maintain clear distinction between the roles of application algorithm developers, physicists, computer scientists, and the framework itself. ERSAP takes care of event transport, vertical scaling of user algorithms, and the composition and orchestration of the application. It accomplishes this through data processing environment, DPE. Here you see, here, those are DPEs, which provide the runtime context for algorithm execution. To integrate user algorithm as an ERSAP actor, it simply needs to implement a straightforward interface illustrated on this lower, lower part. Within ERSAP, user algorithm referred as user engines are wrapped in data processing stations, so-called data processing, DPS here. These stations enable optimized data communications and scaling, striving to minimize data copying, serialization, deserialization whenever it's possible. For instance, data passed through between actors within the same data processing environment, DPE, is communicated by reference, avoiding unnecessary copying and serialization. Data is only copied and serialized when it crosses boundaries between processing environments, say from node to node or from C++ to other data processing pipeline, runtime. Currently, ERSAP supports both C++ and Java bindings. We are extensively working on Python and Julia. So for additional technical details, you can use the links to Git and our latest publications. Okay. Once again, here is the ERSAP data stream data processing pipeline diagram to guide us through the demo that I'm going now to show you. On this right side, you'll see a pipeline that will be horizontally scaled across distributed compute nodes at NERSC, OLCF, and Fabric. The similar pipeline runs a smaller pipeline, writes at Jefferson Lab, for handling reconstructed processed events which are coming back from distributed process reconstructing pipelines. During the demo, we will be doing changing the complexity of the orchestration of the composition of the application by in real time enabling a group of the disabling group of these actors. So this was necessary because our resources were mostly unified resources. They have the same power. It was 90-some% was Perlmutter nodes, NERSC Perlmutter nodes. So then we had 4 nodes at OLCF defined and 7 nodes at Fabric. So here we started when we made a request for 4 nodes at OLCF defined and 80 nodes at Perlmutter, but we had 7 already dedicated nodes at Fabric, and this is what you see. The data is this black line is now moving to the load balance and distributed to those nodes. And then at this point, you are seeing that all the rest, the nodes became available, and the pipelines are running there. What you see upper plot is event rate, the input event rate, and the bottom line is input data rate. So for now, and this green light on this here shows the data coming back to the Jefferson Lab for data validation and visualization and data quality assurances. So as you can see, all these nodes are getting, of course, in this case, so the rates are very low. input rates. So what we are doing, it's not a data acquisition. The source is not data acquisition. It is recorded the data, raw data, which we are replaying and multiple files and streaming this through the load balancer for processing. At this time point, you see that we increased the data rate. Now we are about 12 gigabit per second, and the load balancer is very nicely reacting on our rate changes. And rate changes. This is the load balancer one. Okay, we don't have the load balancer two, which is smaller pipeline. Coming back the data to which I will show on the next slide. Here we started to play with to try to make to understand how it would be the behavior of load balancer when we start mimicking different power processing, different power processing. Some of them, you see these three bands. So the lower part is doing mostly high level, almost complete reconstruction. The rest of the other bands are doing a little bit watered down reconstruction. Some of the and the upper one, at some point we will leave one node which will do simply very naive reconstruction, just simply doing EC reconstruction and heat-based tracking, which is is not that much compute intensive. And all of that was very nicely detected by load balancer and balancing it accordingly in order not to overwhelm the processing nodes. And here's where we're increasing rates again. And you can see that, I may speed up a little bit. So this, what we had 1 hour allocation time at NERSC for that many resources, 80 node resources. Then, oops, sorry what I did. Yeah. So again, at some point we decided, okay, let's so leave some of the nodes and just leave one node, and the rest of them giving equal type of the processing. So this is again. Even here, the processing, there are very few nodes which are pre-scaled in order to do full processing, in order to get the understanding of full reconstruction quality. But the rest are pre-scaled or complexity of the algorithm are decreased. As you can see now, we are at the level of roughly 80 gigabit, and we will be reaching, and was importantly, it was to see the behavior of the system when it reaches the point when then something drastic happens to entire pipeline, say majority of nodes when going blank or just failing, or this will be the time when our hour is achieved, our allocation, and the NERSC will take all our resources away. And you can see that we fairly nicely getting this across that point here. You can see, I can show you. Now we are at 100 gigabit to the distributed among three sites, distributed site along the country, and then at some point we'll see now that the nodes will go away, and those remaining 7 nodes will continue processing, even though we don't have the graph that shows the buffers, input buffers of those processing backplane. So those buffers are completely filled, and it's trying to do the correct thing here. So back into at Jefferson Lab. So do you remember that small workflow at Jefferson Lab that was running through the second load balancer? Here you can see the smaller picture here as well. The black lines are going to, this is the the data for the reconstruction, and then green lights are already reconstructed or processed data going through the second load balancer back to Jefferson Lab, where we are running data quality assurance plots. And on this lower left, there is the important plot that every time we do this pi0 reconstruction peak, missing mass reconstruction of a pi0, which shows that, oh, the data is correct. So reconstruction is correct. And so it can, in real time, you can see the pi0's reconstruction here. And here you are seeing now entire detector, two sectors, sector 1 and 4. There is a electromagnetic calorimeter, pressure, the time of flight, and then the LTC, lower threshold Cherenkov counter, and then drift chambers, and you can see the trucks, right? So even the red ones are time-based trucks, and the blue ones are heat-based trucks, and the particles are nicely reconstructed. Pi minuses, pi pluses, gammas, anything else. So protons, neutrons were nicely reconstructed here. This is a 3D view of the forward detector. So we can see 6 sectors here. All detectors. And these 2 plots are missing central. This is a central detector where you can see the barrel calorimeter, and then with the micro megas, silicon vertex trackers, and other detectors. This is other view of the central detector. You can see the particle tracks in there. And these two parts are showing, this is a time of flight, this is electromagnetic calorimeter separately. So at the end, this was a very successful demonstration of the capability of processing data remotely in a streaming mode in widely distributed compute centers, and bringing reconstructing data back to home institution for persistency and for validation and for further analysis. And there was very important things that we were able to do. This was we're able to do because of EJFAT system. So EJFAT is that what makes this really happen, and we are very excited to have this hardware tool and software tool available for nuclear physics data processing. This successful demonstration and was not possible by very smart people, smarter than I am, that are listed here. I would like to mention Yatish, Stacy, David, Derek, the team from ESNet who make this real to happen, and talented people from Jefferson Lab that were involved in this project. And here is the link. If you would like to contact us for further information, please do so. Thank you. Thank you for your attention.
All right, thank you so much for going through that. So I have allowed anybody to unmute themselves if they want to ask any questions, or if you want to put your hand up, I could acknowledge you. Alternatively, if you just want to ask something in the chat room, you certainly can. I have a couple sort of just to get us started here. So what's sort of the scalability on this? You know, you showed the demonstration using a couple of those sites to do the analysis work. Is there an upper limit on how many may be able to participate in this activity, or have you found what the right number happens to be?
Okay, I don't think we have a limitation, because the horizontal scaling that presents EJFAT system is effectively linear. So we can add as many resources as we would like to this. There are some limitations, but we are far from that limitation that EJFAT system will have. I think Yatish will say if there are the limitations of horizontally scaling. But if we are talking about specific this experimental data to fully reconstruct in real time, so there are a couple of things needs to be happening. So first of all, for real-time processing, complete full real-time processing, we need to have up-to-date calibration constants. And this calibration is something that needs to be done many times in order to get the final calibrations of the detector. Then having those calibration constants, we can do full reconstruction. Assume that we have this calibration constants, and to process class 12 data, this particular experiment data, we need at least 5 times more resources that was used during this exercise. So we had roughly 100 nodes, so 97 nodes or something. We need to have roughly 450 to 500 perlmutter nodes, okay, on the 28 core hyper-threaded in order to fully, to keep up data acquisition rates. Say this one, to keep up 100 gigabit, say, okay, say, no, data acquisition, 100 gigabit rate fully reconstructed. We need resources that of about 450 to 500 nodes to completely reconstruct at this rates. But as I mentioned, in real applications, when we are doing the processing from the experiment, so most likely experiments will not have that many the calibrations done. So we might have real-time calibration pipelines running somewhere. So that might be, but I cannot give exact resource numbers, how much we need to do full calibrations at real time. But I don't think that if there is limitation for horizontal scaling from the hardware perspective, they are way higher than both existing experimental data processing will need.
Okay, thank you. And Yatish, I saw that you on video muted yourself. Did you want to add anything?
No, I think Vardan got it, but let me just highlight something. He answered 2 questions. He answered how many Perlmutter nodes could he possibly want in his wildest dreams? And the answer is still pretty low compared to the total number that are there. So there's like 5,000 nodes, I think, in Perlmutter. Vardan needs 500, so he only needs 10% of the capacity. So between NERSC and Oak Ridge, there's so much compute available that there is effectively a lot of headroom. You could step into a different world where instead of 100 gigabits, they crank it up to a terabit per second, and then they need even more compute. But even that's capable within existing resources, if not more, in the next generation. So on the compute side, there's some sort of wall for scale, but we're nowhere near it. And then on the networking side, the EJFAT, the really clever thing about the EJFAT protocol is that it's a stateless forwarding protocol, which means that it behaves like lag. So if you want a terabit, we just have to have a terabit worth of FPGA ports, and we lag them together, and everything just grows. And so networking-wise, even with existing ESNet capacity, we could carry so much more traffic than the compute nodes could possibly do. So in a hypothetical sense, we could fill every compute node at Oak Ridge and NERSC and Argonne simultaneously, max them out, and still not hit a bandwidth limit within ESNet.
Okay, thanks for adding that. So I guess my next question would be, have there been thoughts about trying to adapt this sort of workflow for other existing science experiments that have a similar sort of pattern where it's a detector or some form of capture and then needing to shuttle off the data to computational workflows, LHC related or whatever? Any thoughts to that?
Yeah, so we have work in progress already with FRIB, which is a totally different facility. We're also streaming from our own light source in Berkeley, ALS. And the folks at APS, at Argonne, are also building use cases against it. So we have four completely different set of scientific user facilities that are using this or planning to use it. And it applies just as well to Slack and Brookhaven and a bunch of other places that we haven't engaged just yet. So the whole idea of EJFAT is that it's agnostic to whatever particular science somebody's doing. It's a generic infrastructure, and there's no changes to the EJFAT implementation to go from one to the other.
Currently, we have a project at Jefferson Lab, another science case where we are designing streaming readout data acquisition, where we will be utilizing EJFAT load balancers locally for event identification and event filtering and frame building data acquisition steps. This will simplify identification of the events for data reduction purposes at the data acquisition level. So it is possible that some of the experiments like Molar or I don't know, some others that will generate so much data, so it will be required that we will not have enough storage to store all this garbage. Effectively, after processing, you might say, okay, there's, for example, some of the data is only a certain percentage of the interest in physics or something like this. But for that purposes, we would like to utilize EJFAT, which will speed up at these high rates and high bandwidths, locally doing, combining all these, I mentioned how the crates which are streaming data from sub-detector components, and they needs to be glued together and do this so-called frame building, and that process will simplify it by using local load balancer, EJFAT load balancers, and then we'll have a processing which might or might not utilize EJFAT to do level 3 or level 4 triggering, where you, for example, create a branch and you look specific physics in the data and mark the data before being persisted. And this will be helping tremendously, speeding up tremendously future physics analysis, where people will not only start digging into the big pile of garbage, but at least they will see some of the markers. They can follow the markers. I like this experiment specific marker to find which was done at the real time during the data acquisition. So this is a very excited project, and we are currently starting this project.
Okay. So we're almost at the top of the hour. Todd Gilbert, you sent me a question, but unfortunately you sent it to my private account, so I can't really read it on my phone. Would you like to unmute and maybe ask?
Thank you, Jason. My question was, what was your major roadblock or pitfall?
Yeah. The experiment, the processing at Jefferson Lab were batch processings. Okay, so the majority of at least my effort and my complications were how to adopt batch processing into the streaming processing pipeline. So that was involved or taking all this. It helped tremendously because that particular class 12 experiment, their processing framework was microservices based, and so I was able to extract their algorithm from there and put into the ERSA framework that I described here. That conversion was as a big time consuming component. And of course, there were multiple roadblocks there in order to make this thing to work. But other than that, I never in so many years in my career, the group of ESNet was, I don't know, this is amazing. So they were responsive every given moment, being at night or early in the morning. So whenever we have any problem, they would respond us very quickly and solve the problems right away.
Great. If we don't have any more questions, I'll thank you both again for giving us your time today. I already have the slides, so I will make sure that those get posted along with the video. And next week's talk is going to be person or office hours. So like we've done in the past, we'll have members of the person or team available to answer questions about just about anything. They don't prepare any usual formal demos or anything like that. So anybody who would like to attend to try to get help with anything, please do so. Thanks again, everybody, and we'll talk to everybody soon.
Bye.